कितने हैं 40 40
Well, good afternoon. I am Dr. Chetan Prakash Kaushik. I was working in nuclear recycle group of BARC as an outstanding scientist and director of nuclear recycle group. I worked almost for the management of radioactive waste for more than 37 years at Tarapur and BRC Trombay put together. And today I will be discussing with you with respect to policies, strategies, and practices being adopted for management of radioactive waste, which is an important nuclear fuel cycle component. So, as I told that I am a Rajaramana Fellow, and in December 2023, I was also confirmed with the Fellow of National Academy of Engineering by INAE. So we'll start with the plan, but we have for another 45 to 50 minutes. Maybe I will just give a glance on the options of electricity available, because this is for the continuity of the subject. And then we come to fuel cycle options available and what India has adopted. And then we call popularly the two main, one we call as a front end of nuclear fuel cycle, and another part is the back end of nuclear fuel cycle. If you broadly divide the whole fuel cycle into two components, two compartments. So if you start from milling, mining, then going for a fuel fabrication, and then for reactor operation. So up to that part we call as a front end of nuclear fuel cycle. And then it is coming as a spent fuel management, which essentially comes as a reprocessing and waste management. So these two components put together is coming in the category of back end of nuclear fuel cycle. So I'll be discussing about the management of radioactive waste, and then some of the works which we have done recently in the last decade, which has really put our country at the driver's seat as far as management of spent fuel is concerned. And it has been a very complex technology, but because we have a what is called defense in depth, which starts from even having a well laid down policies, then strategies, and then we have a independent safety review. All these three things put together has really kept us a very excellent safety record with respect to the plant operations. When I come to plant operations, I will also be discussing how we have achieved through this, because we do extensive what is called job hazard analysis of each component, and then we talk about what scenario possible, and then accordingly we plan a judicious installations of interlocks and all, which has really made the systems very safe in almost last 30 to 40 years from where we have started our waste management and reprocessing. And then these our policies and then strategies along with the practices, again, they're all a science-driven process, because all of us are aware that science is also evolving, and we have been also making refinement in our policies and strategies. If you look at the world about, we have seen at your Fukushima last time, 2012, then also later on worldwide, they have made improvisation so that it should remain a fail-safe systems. So accordingly, we have strengthened all the systems in the back end, and then we will also maybe for a couple of minutes spend how this decade works is being viewed by international scientific community. So with this, here I will just rush through just to give a significance that nowadays, the global warming, what we say, has gone beyond the table of a typical scientist, because earlier, last 20, 30 years, almost scientific community all over the world, they keep on working and trying to publish. But now things have gone from scientific community to policymakers, because there have been a visible change with respect to global warming. This particular slide shows that per person consumption of electricity, if you look at maybe world average is something around 3000 kilowatt hour, that is unit, and in Indian context we have to still cross a big gap, even if we have to come near to the world average. Presently we are at around 1255 kilowatt hour. This is the consumption of electricity units per person in India, and that too also is not a representative sample, because still there is almost 205 million of people where still the light of or the electricity has yet to go. Similarly, the worldwide also there is a 9% of the world population, amounting to 940 million as per the United Nations data, which still need to see the light of the day in terms of electricity. So if we look at that means this shows that this is per person consumption of electricity is directly correlated with the development index, because nowadays I'm sure all of us are aware that we cannot envisage even any activity whatsoever together without consumption or without use of electricity. So world average is around 3000, and if you look at what is called advanced countries, they even touching around 12,000 for US, and even Japan and all around into 8,000. So there's a big gap, and this big gap need to put. And we are all aware that nowadays government of India is trying to put a lot of efforts and focus attention on our renewable part, for the simple reason of trying to reduce the carbon signatures. And if you might have seen even in December also, December probably 21 and 21st December or so, our Honorable Prime Minister Modi ji has visited what is called COP, that is Conference of Parties. That was 29th meeting. It was held in Dubai, where again India has reiterated that by 2070 we have to have what is called zero carbon signature. So that means more stress need to be given with respect to a process which can meet the demand of electricity at the same time without emission of any carbon. From that point of view, the solar part has been given good attention, but we are all now aware with respect to the limitations of solar. Maybe it is not that easy to meet the baseline voltage of the grid. At the same time, huge amount of toxic waste also will be coming, and solar panels, over a period of time, they need to be replaced more frequently, generating a large volume of the waste, and that too also with respect to chemically toxic constituent. That means presently we are focusing on what is called energy mix. But nevertheless, this particular slide shows about the greenhouse gases. And when I say greenhouse gases, I particularly mean CO2, CH4, and NOx and all. It is really very surprising to see that 99% component of the air, and they are not at all contributing anything with respect to global warming. And CO2 in particular, maybe if you look at before 1900, the data shows the average, our atmospheric average concentration of CO2 was something around 200 ppm, and last maybe 100 year or 125 year after the what is called industrial revolution, and that time onward there has been a sharp rise in the concentration of CO2, reaching to something around 400 ppm. And CO2, we know that whenever the IR radiation comes, which is nothing but the molecular fractional part which is generating heat, and CO2, N2O2, which is a major fraction of air, they do not absorb CO2. I can recall, let us recall our BSc science and all, for IR to absorb, there has to be a change in dipole moment. So from that point of view, it is the CO2, maybe methane, and then NOx, but it is the CO2 which is present in large amount, and it absorbs IR radiation while they are getting shined to the earth. At the same time, even after reflection from earth, then going back again, they are being absorbed by our CO2, which in turn makes the earth more warmer, and all of us are aware about the consequences of this particular part. So now indications of global warming are more than visible. We have seen the changes, abrupt changes in the environment and all. We are all now aware that your melting of ice, glaciers and all, increasing the rise of the sea level, and eventually paying a heavy price. So all of us are aware by this time that need efforts and honest efforts need to be put while meeting the energy demands with respect to having zero carbon emission. If you look at the process available, when we talk about renewable, wind anyways are there, but if you look at the capacity factor of wind is around 25% only, and if you look at solar, maybe all of us are aware that nuclear goes to as high as 90% of this. And when we talk about nuclear, just to give an example, even if you look at the 1 gram of uranium-235, which is our fuel for nuclear technology in something comparable to coal in a typical thermal power plant. So 1 gram of fissile uranium-235 is equivalent to almost energy coming from 2 tons of coal. That means a huge amount of energy reserves are available. So we in nuclear family, we say we split the atom for the societal benefits. And just to cover up that, nuclear technology is not only meeting or trying to put getting the carbon or green energy, but at the same time, it is offering its advantage in almost every sphere of human life, straight away getting the advantage of science and technology reaching to a common man in terms of health, food, water, and national security and industrial. So many applications are there, almost it is touching. And really it is unfortunate. If you look at the fission discovery, it was in 1939 when Strassman and Otto they published the first paper indicating the fission reactions, but not many discoveries in the world around has a beginning from a destructive purpose. So 1939 it was seen the discovery, but at the same time it had a destructive application in the World War II. All of us are aware in Hiroshima and Nagasaki. And so the first use when started from a destructive part, it has really had a deeper impact on the individual's mind. And whenever now we talk about nuclear technology, inadvertently our mind straight away goes to the destructive purpose part. But if you look at the reality is different. It is really the atom is getting split up for touching almost every sphere of life. So now we look at the fuel cycle options. We are having 2 types of fuel cycle options. One school of thought, they go for what is called open fuel cycle, where they take uranium as a fuel, they put into the reactor, and maybe by this time when the course is in advanced stage, you have been knowing that there are 2 competing reactions that are going in a typical nuclear reactor. One is called a nuclear fission reaction, where the fissile atom, particularly if you talk about natural uranium, it is 235, which is interacting with the thermal neutrons and giving a fission product plus huge amount of energy. And that energy converts the coolant and the water into high pressure steam, which in turn rotates the turbine of generator. Nevertheless, 238 uranium is also not sitting idle, rather it is also interacting, but may not be giving a fission reaction because energy is thermal range of neutron, but it is called neutron activation, and we get because of this another very important fissile material called plutonium-239. And this is a very strategic material, not valuable. There is no price tag available for this material, and it is very important fissile reactions as a fuel for future reactors. So there are 2, one is called closed fuel cycle and one is open. A time comes in the reactor when the content of 235 gets reduced as a function of time, and it may not be easier to contain or to continue the nuclear fission reaction, and we call now this is a spent fuel, something equivalent to a typical ash in a thermal power plant. And then the countries who are going for an open fuel cycle, they say, okay, now this is a waste. And actually it will contain fission products, and it will contain plutonium-239 also. Just to tell you that plutonium-239 is having a long life of around 24,000 years. So those countries who go for open fuel cycle, straight away that waste is, the concept is that will be disposed of something around maybe 500 meters below the earth. In the typical regions, we say is a geological disposal facility. But the countries, including India, is leading that school of thought. They say no, spent fuel is a material resource. Rather, they go for a chemical processing. They remove the plutonium formed. They remove unused uranium, and at the same time, they even separate fission products and try to deploy them for different societal applications. This is the work which has been done in India for last 1 decade, and almost it amounts to almost near zero waste, which has put India on the driver's seat in this particular complex technology. Look at the fresh fuel. When we take it, goes to reactor, and once it comes spent fuel, being a closed fuel partner leading the group, we say okay, we take it to called a facility called a reprocessing facility, where we dissolve the spent fuel and then go for a chemistry driven process which is called solvent extraction, and there we remove uranium and plutonium, try and then deploy them for as a fuel for future reactors. And not only we stop there, rather even the fission products, which were normally once upon a time were called as a waste, we separate them and then deploy them for different applications. Then there is a one part called actinides, because in the reactor, plutonium-239 also picks up a neutron, gives plutonium-240, which is again a beta emitter, gives americium-241. So if you have seen your periodic table, at the bottom, there are two parallel lines we call as the lanthanides and actinides. So these are the actinides what I'm talking about, americium, neptunium, curium. So they're also produced in the reactor during the neutron activation, and they are important in the sense they are either they themselves are long-lived or their decay product is long-lived. The countries who are going for an open fuel cycle, and while disposing the waste, the active content will remain in the waste for a time scale which is really very, very long in nature. Maybe millions of year activity will remain, because these are long-lived, but Indian has gone for separating these actinides and try to utilize them for strategic as well as different industrial applications. I'm just coming the high-level waste, how it is getting generated. In fact, we define the waste as a typically low-level waste, intermediate-level waste, and high-level waste. These low, intermediate, and high-level, these terminologies are coming depending on the concentration of radioactivity, radionuclides. That means the radioactivity which we measure in terms of either Curie or Becquerel, and then half-life of the individual radionuclides. So it is the high-level waste which contains almost more than 99% of the radioactivity getting generated in the entire nuclear fuel cycle. So I thought let us start with our HLW, that's called high-level waste. I have shown is a red nature because it needs a complex process. It is heat generating also, because the radionuclides are unstable, they are trying to decay, and so while decaying they are emitting radiations. As a result, heat is getting emitted. So even storing also needs a cooling facilities and all. So the red nature shows it needs a systematic and careful investigations, and then trying to put a process methodology for management of it. So the fuel initially is chopped, we dissolve, and again go for a chemistry to change the valency, because in a solvent extraction, which is typically a chemical engineering driven process, we have to play with the valency of the radionuclides. We convert Pu, that is plutonium, into +4 stage, uranium into +6, and then we go for solvent extraction using one of the organic extractant called as a tributyl phosphate, and dodecane, normal dodecane is a diluent, and of course the liquid will be HNO3, because we are dissolving the spent fuel in nitric acid. So by this solvent extraction, we remove uranium and plutonium, and then whatever is left is fission product, it is concentrated, and earlier it was called a high-level waste, but this also then subjected for different separations. We individually remove the different fission products, and then depending on their property, we find a suitable use. So this is also very importantly contributing in called circular economy. I'm sure the audience here may be knowing the difference between linear economy and circular economy. If we have to look for a development on a sustainable basis, we have to devise a process which gives us what is called circular economy. Maybe if we look at the father of Indian nuclear energy program, I'm sure like this slide might have been repeated number of occasions where Dr. Homi Jahangir Baba. But one important thing I have to add that conception or the importance to waste management has been given right from the day one. And then as per him, as per his preachings, we had to have a very safe management of radioactive waste to a standard where which can other countries can emulate, and India can remain as one of the reference country in terms of management of radioactive waste. Look at the classification. If I go the waste, I'm sure you will not find any process where there is no residue left. In addition to the main product. Now this residue, since somehow, why we say waste? Because we were not able to find any immediate use, or it would not be economically viable to convert that product into a useful product. So we used to call as a waste. And so there is no any industrially done activity where there is no residue or so-called waste possible. So to that extent, nuclear industry also is not an exception. Here also we get a small volume of waste, which is sometimes in liquid form also. Solid waste also, we divide solid into two parts, combustible and you can say non-compressible as well, and of course gaseous waste also gets generated. Coming to liquid, we primarily, as I was mentioning, divide in three parts, namely low level, intermediate, and high level. Now this slide particularly shows the management strategy for high level radioactive waste, the HLW from reprocessing. So by this time we know from where high level waste gets generated. It is getting generated during reprocessing of a spent fuel, and where U and PU, that is uranium, is removed, and then high level waste is stored into high integrity stainless steel tanks underground, and then there is an underground provision for transfer of this waste into a waste management facility, maybe at a distance of something around 150 meters. So there is an underground pipeline, which is a pipe-in-pipe concept, so that there is no chance of any leakage of high level waste during transfer. So those pipes and all are well qualified, and after a lot of review, the cooling facilities and all, and then the waste comes to the waste, and the liquid waste comes into the waste management facility, and there the liquid waste is converted into a inert solid matrix. Inert means even if the radionuclides, they get chemically bonded to such an extent that they become almost chemically inert, they become immobile, even if they come into contact with water, because water is a carrier medium by large. So even if they come in contact with boiling water, they are not getting leached out from that solid material, so that they cannot reach to human environment until they decay. One of the good advantages of this radioactive part, that the hazard potential does not remain constant, rather it gets reduced as a function of time, primarily depending on the half-life of radioactive material. So now question comes, what is that solid matrix? So that solid matrix was glass. So we convert high-level radioactive liquid waste into a glass matrix, a glass product, and that glass products serve as a host to retain the radionuclides for a time scale where they will become almost innocuous level decay. And so this particular picture shows the pouring of the glass into a canister, and needless to mention that all these activity is done in a plant in a what is called hot cell. Hot cell is nothing but a thick concrete cell, maybe like a mini football ground. There will have a different engineering components, and the thickness of the wall is something around 1.2 meter of concrete, so that whatever robotics or whatever inside activity we do, our operators is standing outside and they will not have any exposure whatsoever with respect to the radiation part. So we convert the high level waste into glass product, and then that air-cooled storage where you are finding the stored glass product, because radionuclide is there and still they are generating heat. because of they are decaying. So heat need to be dissipated. So they are now being stored. And the good mechanism to your cooling is there is a passive cooling, because the heat generated will make the surrounding air lighter, and the lighter air will go up and to take the gap, the space, fresh air. So there is a circulation, there is a air draft will be getting established, so that air will be dissipating the heat. And once the heat is dissipated, they come to a, you can say, near ambient temperature, and that time they will be disposed in geological disposal facility. But in our case, now when we are removing all the radionuclides, including fission product, our inventory of the waste is almost nearly zero. Now question comes to what is so special in glass? Why and the glass is chosen as a matrix for accommodation? And then this again, glass, if you look at, we have learned from the nature. If you look at maybe even in Bombay near Thane, we have in an area where it is from the Survey of Geological Survey of India, they told that maybe 65 million years before, some nitride and all have fallen, and in earth we have silica and all the constituent which can form a glass. So their natural glass were formed. And like this, there are many sites in the world. Those glasses were investigated in detail and found that there has not been much loss in the integrity of the constituent in spite of a long length of time. Clearly indicating, the nature is indicating to a nuclear scientist, look, glass can be very effective host for retaining their nuclides for the time or the length of time scale what we are looking for, till they decay to almost unnoticeable level. Now, if you look at the waste management part, it is a good hybrid of science and technology put together. We need to have understanding of separation science, because I was mentioning that we are separating. That means we need to understand the minute difference and then try to explore those differences as a technology for quantitative removal of those radionuclides if we had to deploy them for any societal benefits. Material science is very important, nuclear chemistry. Similarly, on the technology side, as I was telling, robotics is very important, because any maintenance and all need to be done inside the hot cell. A lot of material handling is required. The canister had to be taken out. It had to be remotely welded. So those all things need to be done through remote handling systems. And the glass technology, many of you may be knowing glass appears as a solid, but it is not a solid material. Like it's amorphous material. So the glass technology itself, nowadays you may be knowing that even 30-40% of our glass products are being seen in our construction part. And even the 5G, 4G and now internet and all, fiber optics again is nothing but again a gift given by glass technology as such. This is a typical process flow sheet where I was talking about we do extensive what is called job hazard analysis, or hazardous operation. We go and then we try to check what worst may happen. Even the smallest thing that, okay, this all is done in a hot cell, and let's suppose the class 4 supply has gone. When I say class 4 supply means normal power supply, let's say it has gone. And the hot cell is normally kept as a little negative pressure compared to outside, so that the diffusion, even by diffusion also, radionuclide does not come. So in case when the class 4 supply goes, then DG set need to come. But even if, let us suppose, okay, DG set takes maybe some 4 seconds, 5 seconds and all, but if because of some reason or the other, even if DG set doesn't come, then what to do? So those sort of class, your worst scenario, we after taking, then we put all our interlocks so that we can avoid any what is called mal operations. You know what typically happened in Fukushima because of tsunami. Even the class 4 supply anyway has gone because of your earthquake. But even the DG set, the water layers coming from sea is so high that it has buggered up all the system of even our DG sets. As a result, cooling could not be given, and then it resulted in that the water got converted to steam, and high pressure steam even reacted with our metals like your zirconium and all. So it was a chemical reaction. Not a nuclear reaction. Zirconium reacted with water, steam, and hydrogen metal reacts with water at high temperature, pressure. It becomes a hydrogen, and it is the hydrogen which really made the explosion to happen. And then it was followed by when core became open to atmosphere. And then there was activity and all what got released. So what I'm trying to tell, we do extensive job hazard analysis of each component, and then try to put the interlock system. This particular shows that again the design stage itself. This is a temperature. It's a melter. It's based on induction heating. Glass is to be made at high temperature. No, so glass goes almost 1000 degrees Celsius. Now you have a different options for even heating. Start from even your resistance-based heatings and microwave heatings, and here we have gone for induction heating. So the design is such that we should be able to do maintenance as well as operate remotely. We need not go into the cell, because cell going should become a once in a blue moon activity. Like WIP Trombay, waste management plant Trombay, it was inaugurated by that time our Prime Minister Atal Bihari Vajpayee ji, and still till that time 2002 onwards, now almost 22 years are over, we have not made any entry into the hot cell, because the design was such that is such that we are able to do all the operations and maintenance from outside, and with the help of remote handling gadgets we have installed in the plant. Look at the waste if we contain, it is having a lot of inactive chemicals, because those chemicals are added during reprocessing stage. Like I was telling, we are playing with the valency and all. Valency change ke liye to you have to add some chemicals, no? So those chemicals and all, they increase the load of inactive waste. And inactive waste management, we have a different process altogether. So what change we made in last decade, that we started removing the inactive waste part. And how to remove, rather than which is almost 80-90% component, let us remove the small component, which is radioactive waste. We kept on removing all the radioactive part, and then inactive part we have a different process altogether. So this process has really helped us from many angles. One angle was, let us suppose look at the country's fate who are going for open fuel cycle. That will contain Pu, that is plutonium, uranium, and all. So there, the upper line, that is which is equal to your yellow line. This particular line shows that if you don't remove anything, then it will take almost more than a million years for the activity to come to a natural uranium level. This red line shows the natural uranium level which is existing in nature, and human civilization has been coexisting along with uranium, natural uranium. So the activity of the waste, if you don't remove anything from there, the way in open fuel cycles are coming, even if they are disposed at the depth of 500 meters, that's what is being conceived, still it will take a huge time, more than 1 million years, for coming to decay to a level where activity comes below equivalent to natural uranium level. So we remove your closed fuel cycle, we remove uranium and plutonium, the time gets reduced from 1 lakh to almost 10,000 years, even less. And then if you remove the fission product, then even comes to less than 300 years. So the removal of this part also helps immensely for reducing the toxicity or the burden on the mothers as well. You look at the reduction in long-term radiotoxicity, and then they can be minimal for transmutation. Transmutation means we can again go for a high Newton energy to force them to undergo fission that time. Look at the upper side. This particular your plant is a facility located at Tarapur. Where we have developed the process and removing actinide, which is a long-lived material. And this plant is the first of its own kind in the world, where engineering scale separation of Americium-241 is done. And I don't know many of you are aware or not, this human Chandrayaan-3, this Americium-241 as a heat source, it is an alpha material. It was given to ISRO because that keeps the semiconducting devices in the warm condition. And those who are aware, they may be aware that if the temperature is in minus and all, the semiconducting device performance comes to almost sees down, and that virtually it decides the usable life of a typical satellite. So this Americium-241 was given by DAE. I'm sure you must have seen our statements from our chairman and ISRO and all that, yes, it was given by BRC. And second part, the fission products, the cesium-137, and this again, the process was developed at BRC. We removed these fission products and utilize them for different applications. And look at, while removing everything, the waste almost is nearly zero compared to a long part if you are going for an open fuel cycle. So the innovation also helps a lot to minimize the volume of the waste getting generated, which comes to nearly zero if we have a, and then this is one part, and secondly, whatever we have removed has got market value. You talk about cesium-137, you talk about strontium-90, look at cesium-137, and these are not concept. Almost lakhs of curies, I repeat, almost a lakhs of curies of cesium-137 has been removed, put into a non-dispersible glass form, and they are now being used as a blood irradiator. Now you may be knowing why blood, why you may be thinking why blood to be irradiated. You know, for an immunodeficient patient, if the blood has to be transfused, so then it has to be first irradiated to destroy all the harmful system, bacteria and all from there, because the immunity of that patient is nearly zero. So the blood irradiation, earlier it was cobalt-60 which was used, and cobalt-60 has got a half-life of 5 years. Again, for making cobalt-60, one has to go for reactor. Here it is coming as a waste and we are removing. So waste is becoming a wealth. And similarly, strontium-90 is being used as a therapeutic applications. In fact, every week we give this strontium-90 to Tata Memorial Hospitals for therapeutic applications for our cancer patients. And americium-241, as I mentioned, space applications. And this is not in the concept. Already it has seen the light of the day when Chandrayaan-3 was given for this. And ruthenium-106 is one of the very recent, maybe 3 to 4 years, a breakthrough where ruthenium-106 we again separated from waste, electro-deposited on the silver plate, and this silver plate was then used for eye cancer treatment. Question comes, why cesium-137, as I mentioned, because it is a much long half-life compared to cobalt-60, and it is coming from the waste. Look at giving cesium-137 after removing from waste, converted into a glass product that is a non-dispersible. Because in hospitals, you know, we don't have a high level of security and all. Tomorrow some terrorist comes and they remove and put into water and all that. So, but here it was converted into glass. Even if it comes to the wrong hands, the cesium-137 cannot come because it has become a permanent part of structure of glass, and that means it is providing nuclear safety and security while using at hospitals as well. So this was also, as the bottom part shows, our country was the first in the world where the recovered huge amount of, because it is not a question of only publishing a paper. Here it is a plant scale where lakhs of curies of cesium-137 is removed, converted into a glass which is non-dispersible in nature, and then more than I think 20 to 25 hospitals in the country are using this cesium-137 as a blood irradiator. This particular thing is a ruthenium-106 being used for eye cancer treatment. You will be surprised, there was only one country in the world, at Germany. The company name is Vivek Germany. You can see in the Googles and all, they were providing this part to almost remaining part of the world at a very, very high cost. That means in Indian context, it was costing around 12 to 15 lakhs per plaque. This is called a plaque, where the is almost diameter is very small with the eyes diameter, and then where we are putting ruthenium-106 by electrodepositing on a silver plate. So this was costing almost some 12 lakh rupees. Almost the treatment was going away from the reach of a common man. In BRC, we developed it, gave to initially to our AIMS Delhi. Initially any change is registered. So there also we gave, but I also went to AIMS and gave a lecture to them, and then tried initially we supplied free of cost, and now last 3-4 years they have stopped all their they were importing it from different, now they have stopped all imports, even Shankar Nethralaya and other leading hospitals. Probably now more than 500 patients have got the advantage of this indigenous technology at a very, very affordable cost. This is almost 50,000 rupees compared to 15 lakhs what they were importing from other countries. And similarly, strontium-90 also we are recovering for different hospitals, and we work on again on what is called develop demonstrate and deploy. And this is the facility where we go for our interim storage of the glass product, where distribution of heat is there. Convection based cooling system is available. This facility is operating at Tarapur and in the southern part at Kalpakam. And this is a typical conceptual disposal part, although India is not doing this part, but open fuel cycle, they have to dispose in a deep, something around 500 below the ground. And there again, India also is doing R&D, but our waste volumes, at the same time, our technology now has really made to follow what is called circular economy, where hardly we have any volume of waste going for this above things. Now, intermediate level waste activity is low. Again, we go for what is called ion exchange, and we try to work even for low level waste where concentration is too low. We work for what is called near zero discharge, rather zero discharge. Waste to water approach. In fact, after the waste treatment, whatever liquid comes, it is being checked, and even the acidity level comes below than what water can be drinked. That means by WHO limit, the activity comes much below than what is the permissible limit of a potable water. So we say waste to water approach, working on zero discharge to the environment by our chemical treatment. Again, it's a hybrid process. We go for a chemical treatment, we go for a ion exchange, we go for reverse osmosis, and other advanced processes as well. For low solid available waste, we go for a volume reduction by plasma incinerators. This is a recently developed in BRC, where the waste volumes is reduced to a small value and then it is being polymerized. Look at when we are thinking, is it not possible to this technology what we develop, what is being developed by Indian nuclear scientists, is it not possible to look for even non-nuclear solutions? A typical burning example is the management of a municipal solid waste. This is a photograph of a Ghazipur, Delhi, where the height of this municipal solid waste is almost not far away from Qutub Minar, and presently landfill and the open incineration is the process being adopted, which is not the best, because this polymeric waste, when you incinerate by normal conventional means, the poisonous and highly toxic gas like dioxide and furans, they come out having very, very small threshold limit values. So these are not the way by which, so advanced process now BRC is doing at a capacity of 50 kg per hour. Once it is done, maybe this will be acting as a model plant for all the states, and the time will come when this process will be deployed in almost all the states for this. And more importantly, though, this all municipal solid waste, they have a calorific value. A 1 kg of this waste, in fact, each gram, something around 2000 calories per gram is the calorific value of this municipal solid waste. Even all these non-degradable polythene and all, see what they are. Ultimately, they're all carbon, hydrogen polymers. If you heat, they're all exothermic. That means energy comes out from there. So those energy is also being utilized by our plasma process, and this energy uses converting water into steam, and then that steam also can be utilized. So this also is a part of our circular economy. This is a small volume of waste which will be helping for disposing the part, and there are low half-lives where the waste within a period of some 30-40 years actually comes to a innocuous level. I was telling about the policy strategy, and then how to make sure that is a fail-safe process. So these are all again science-driven process. So based on a lot of experiments and all, we follow the acts and rules, maybe Atomic Energy Act, Atomic Energy, that is called our rules 1987. These are all, what I'm trying to tell, these are all independent safety review. And at the same time, these policies and strategies are all have come to a asset test by having a job hazard analysis for each components, and then preparation of regulatory documents, taking approval at multi-tier based independent review and multi-tier based safety approvals. We do come across some sort of a deviation from this. For example, in case of a failure of a class 4 supply, and the activities if DG sets comes, it takes time, then there will be a diffusion from the cell to outside, and that time online health physics instruments are in place. They'll find, okay, now activity level is rising. We call it DSC, that is derived air concentration, and at more than some 10 DSC, they'll say, okay, now this is called an emergency situation where the operators who are working can go out, and then the things can be resumed back once our DG sets and all they come to operation. What I'm trying to tell, there has been a systematic approach to deal with the situations, and they're all being discussed and deliberated in the regulatory committees which are independent. They are not the part of operations. So again, followed the close. I'm going to the now what is called some sort of a your conclusion part of thing, that our policies, then strategies, they have been developed over a period of time based on the science and technology. We do also hazard analysis so that we can avoid any undue call for operation consequences in case it comes, because all processes have been done initially on the laboratory scale, and then we see 1-to-1 before the plant is made hot. Similarly, so we minimize the segregation of waste to be practiced. We have a graded approach for regulation of radioactive waste shall be followed. Discharge and disposal of low liquid waste. See, we do with the zero discharge part, and maybe how we are now viewed by internationally. Look, the one last decade part has really taken almost as a surprise by our international community. They were telling, when they came, they were finding that, okay, we need your help, and we really, because we have made waste as a wealth. This was not being practiced earlier, and several of this part we were first in the world. So this is similarly in a what is called USNRC. They were also telling it is impressive to see C137 recovering from waste and made as a sellable product, which will really affect overall economics of nuclear science and technology, leading to a circular economy. Similarly, we have a CA France. These are the two, CA France is a big player in nuclear science and technology. When they came, they were also quite impressed with respect to this, and they were looking, okay, they can be used for as a medicines. They were highly impressed with this. And in Japan, they told, we need your help in Japan. Look at the things once in last one decade, how things have dramatically changed. And now Indian scientific community is almost sitting at the driver's seat for this complex technology. Maybe somebody almost indicating some sort of a recap of what we were talking about, that we have enough and enriching experience in a regulatory part, and all these regulations come to a vast experience of science and technology, and we have gone for a closed fuel cycle where we reprocess, because we found that reprocessing is for optimal utilization of our resources, And now waste we have converted into a wealth part. In fact, on the other day, the chairman of our Atomic Energy Commission were telling that the name of the division should be changed to a wealth management division. This is on the lighter part, that each component of waste is being separated and now converted into a product. So India is having now successful beginning of partitioning. As I told, Uranium-241 is removed from waste and being used. One example was our space technology. Safety is prime concern. The best track record with respect to safety is the result of adoption of safe practices along with continuous, exhaustive, and independent regulatory review. That's the main crack of this, that how we are able to go for almost an excellent safety track record. Of course, this is the last slide. This particular I always use as an outreach program. That ring what we are seeing. This is the volume of the waste. I repeat, this is the volume of the waste which will be coming out from radioactive waste part if entire Indian family uses all electricity requirement from nuclear technology. So throughout the year. So that means the volume of waste coming out from nuclear technology is nearly zero. That's why we call it is a renewable energy, and it can meet the power grid requirement, the base voltage of grid requirements and all. And the way our Honorable Prime Minister has promised, by 2070, we'll go for a zero carbon. I'm very sure nuclear technology is going to play a very important role for developing the nation on a sustainable basis. With this word, thank you very much for your patient listening, and it will be my pleasure if questions are there on this. It will be my pleasure to discuss this. Otherwise, my email ID also is available, cpk or small at the rate barc.gov.in. It will be my pleasure to discuss about those, and even if some questions are there, and if organizers permit, it will be my opportunity or my pleasure to discuss them as well now. Thank you so much. Yeah, this is provision, no? They can write here questions में था ना, बिठाया कुछ लिखा किसी ने? Attendance पर. अच्छा अच्छा. ये ले लो. Any queries, please mail me to cpk@barc.gov. I repeat, if we have any queries, please do not think twice. Please email me at the email ID cpk@barc.gov.in. Okay, I can try here. आएगा अभी? कहाँ पे? नहीं आ रहा. हाँ आ रहा. cpk@barc.gov.in. So this is the email ID for any questions, for any queries. For any queries. For any queries, right?